Okay, so we're talking about section 3.3, day one, and it is a little bit of a challenging concept to begin with, and it has a little bit of challenging algebra in it, but luckily we have a day two coming up. So we're going to just deal with the beginnings of this idea of implicit differentiation. So if you remember, every function that we've been taking the derivative of has started out y equals or f of x equals, so that our function was explicitly stated, and the terms that were over on this side had an x in them if this was a function with respect to x. So all the x's were on the right and the function name was on the left. What we're going to talk about today is ideas like x squared plus y squared equals 4. That's not a function because it would fail the vertical line test. However, it is a relationship between x and y, and it is not one that we could actually solve for y, because if we tried to solve for y and make it say y equals, we wouldn't be able to because of this ambiguity on whether when I plug an x value in, I get a positive y or a negative y. There's two answers for every x value that I plug in. But it doesn't mean I can't take the derivative with respect to y. I just can't solve for y and do it explicitly. I'm going to have another way to do it. So basically, when your y is a part of a bigger picture and you can't get it all by itself on the left-hand side solved for, you're going to be looking toward this implicit differentiation. So the circle here has slopes of tangent lines that we might be interested in figuring out. We might want to know what the slope of the tangent is at this point AB. So what we're going to do is we're going to use this kind of a notation, dy dx, that's the derivative of y with respect to x, such that is this vertical line. And then we're going to plug in a value for a and a value for b, and that'll tell us the slope at that particular place on this graph, which is not a function. And I'll put a little n here, that should be in a small vicinity around AB. We can look at a piece that is a function. So even though the entire thing would fail the vertical line test, if I took a little snapshot around AB, we could act like this part of the relation is a function. And that's the idea behind implicit differentiation. We'll just look at a little piece so that we can act like it's a function. So in order to do this implicit differentiation, we're going to treat y like it was a function of x, because we've only cut out this part of it. We're not going to consider the entire circle, just around where we want to know what the slope is. So we'll treat it like it is, and we'll solve for dy dx. Since we can't solve for y, we'll solve for dy dx. So it looks like this. You're going to go left to right, and everything you encounter, every term you encounter, terms are separated by addition or subtraction, you're going to differentiate. And the mantra is with respect to x. Everything you differentiate with respect to x, meaning x is the variable, not y. Y is the function. So when you differentiate differentiate x squared, you get 2x. That's the simple power rule. When you differentiate y squared, you don't get 2y. You get 2y times dy dx. That's the chain rule. It's like the mystery functions. I don't know what the function is, but I do know I can use the general power rule on it. And I can move the 2 down in front, drop the degree to 1, and multiply on the derivative of y, which is dy dx. And then I take the derivative of 4, which is 0. So this relation ends up looking like this when I take its derivative with respect to x. And then all I have to do is use my algebra skills to solve for dy dx. So I subtract 2x from both sides and I get to here. And I divide both sides by 2y and I get negative 2x over 2y and then negative x over y. So this is dy dx once I've solved for it. This is the rule for the slope anywhere on the circle. All I have to do is plug in the x value and the y value, and I will have the slope. So in other words, at the point 1 square root of 3, the slope of the tangent line is negative 1 over radical 3. That's what the rule says. And here at 0, 2, the slope of the tangent line is 0 over 2, which makes sense because it's a horizontal tangent. And here, the slope is undefined. 2 over 0, negative. Sorry, I forgot my negative. Negative x over y. So here it didn't matter, it's still 0. Here it doesn't matter, it's still undefined. But I have this rule, and it'll tell me anywhere I want on the circle what the slope is. So the idea behind these rules for implicit differentiation is that if you do d dx, so you're taking the derivative of x to the 6th, that's the simple power rule. But if you do d dx on y to the 6th, that's not the simple power rule because you're taking the derivative with respect to x. So you'd have to move the 6 down, change it to a 5, and multiply on the derivative of the function, dy dx. And that's the thing we're going to eventually solve for. So this rule says that if you take the derivative with respect to x of y to a power, you get that power times y to the 1 less power times dy dx. So that's the biggest thing to remember in implicit differentiation, the difference between x and y when you're differentiating, because you're differentiating with respect to x. So if we practice a couple problems here, the first thing to think about is what rule are we going to use? And we've got x squared times y to the 6th, so we're going to need the product rule as we go left to right and take the derivative of what's on the left and the derivative of what's on the right. So the product rule, if x squared is my first function and y to the 6th is my second, the derivative of x squared will be 2x, but the derivative of y to the 6th will look like this, just like we did up here, 6y to the 5th dy dx. So now we're going to do the product rule. We're going to multiply that first diagonal. We're going to add on multiplying the second diagonal. And then we're going to set it equal to the derivative of the right-hand side, which is 0. And now we're going to solve for dy dx. So to solve for dy dx, we need to move 2xy to the 6th to the right. There's still dy dx here. Negative 2xy to the 6th. So this moved to the right. And then we're going to divide both sides by the coefficient of dy dx, which is this whole thing, 6x squared y to the 5th. Going to divide it away onto the other side. And then simplify negative 1/3, x on the bottom, y on the top. This is now my rule for the slope of this relationship anywhere in its domain. So look at the next one, and you can pause this at any time and look back at it. I'm just going to roll through it. We've got a product rule here a product rule here, a simple power rule here, and constant rule there. So I need to take the derivative of all of that left to right. So I am going to grab another piece of paper here and write down the pieces for the first one. We've got x squared and y, so we need the derivatives 2x and dy dx, which is the derivative of y. So our product rule says we're going to get 2xy plus x squared dy dx. That's the derivative of this first one. Now we'll move on to the second one, and we're going to do the product rule on x times y cubed. Derivative of x is 1. Derivative of y cubed is 3y squared dy dx. We're going to cross multiply for our product rule. We're going to get plus, that's this plus, I'll just multiply these two, 3x y squared dy dx plus this diagonal, y cubed. So we did the product rule twice. This one gave us these two, this one gave us those two, and now we're going to take the derivative of 3x, which is 3, and the derivative of 5, which is 0. And we get to this problem. So now here's the thing. There are two dy dx's, and I need to solve for them. So what I'm going to do is I'm going to look at all the terms over here, this term, this term, this term, and that term, and that term. So there's 5. And I'm going to only keep on this side the two terms that have that dy dx in them. So these two terms are going to stay on the left-hand side. And 2xy is going to move to the right. And y cubed is going to move to the right. And 3 is going to move to the right. So they'll all change signs to move to the other side. And then I'm going to have to factor out the dy dx from the left. So I'll be left with x squared plus 3xy squared. So each of these I'm factoring out dy dx. And the reason I'm doing it is my last step to solve for dy dx, I need to divide away this x squared plus 3xy squared. Divide it on both sides. And now I've solved for dy dx. It's this big mess of an expression that if I plug in a value for x and y that's on the graph of this, it'll tell me the slope. So this is the rule for slope at any point that you give me. But you got to give me the x and the y value of the point for me to plug in. So product rule, simple power, constant, and then after that it's all algebra. Solve for dy dx. So for number 3, not quite as many terms to start with, which means not quite as many terms once I take the derivative. So going left to right, I encounter this first, and that is something that requires the product rule because it's a function times another function. And in order to get the derivative, I need the product rule. Derivative of x is 1. The derivative of this is 5y plus 2 to the 4th times the derivative of y plus 2, which is dy dx. So the product rule says 5x y plus 2 to the 4th, because I like to put these in order, x and then y, dy dx, plus the other diagonal, which is just y plus 2 to the 5th, equals 0. So now I only have one dy dx, and that's going to stay on the left-hand side. So it's got to stay with all of its factors. This is all connected into one clump. And the other term will move to the right with a negative in front. And then I'll just divide away these two factors from the left-hand side so that I can solve for dy dx. So when I divide them away on this side, the y plus 2 to the 5th over the y plus 2 to the 4th, I'll just have y plus 2 on the top, my 7, and then my 5x on the bottom. And this is my rule for slope on this curve. So you can tell it's undefined. When x is 0, it's equal to 0 when y is negative 2. This rule for slope can help you figure out what's going on with the curve of this graph. And the last one, just a little different kind of question. What is the slope of the tangent to the curve at the given point? So that would be also expressed this way. What's dy dx, the slope of the curve, when or such that you use 9 for x and 16 for y? So that means I need to look at this function and go left to right, implicitly differentiate everything I encounter when I do that. So the derivative of the square root of x is 1/2 x to the negative 1/2. The derivative of the square root of y is 1/2 y to the negative 1/2 times dy dx, because you got the derivative of y, and we're doing it with respect to x. And that's supposed to equal 0, the derivative of 7. So now I can solve for dy dx, and then I can plug my 9 and my 16 in. Or I can plug my 9 and my 16 in and then solve for dy dx. I can do it either way. So I'll show you if I just solve for dy dx, what I would do is move the negative 1/2 x to the, or move the 1/2 x to the negative 1/2 to the right where it's negative, and then divide both sides by 1/2 y to the negative 1/2 to get rid of that coefficient. And so here's dy dx. It's the rule in general, and the 1/2s, the negative 1/2 and the 1/2 will divide out, and I'll be left with negative x to the negative 1/2 over y to the negative 1/2. And since they're both negative exponents, I can switch. I can move these to the bottom and those to the top and not have negative exponents anymore. So that would be a nice rule to plug into. I'll plug in 16 for y and 9 for x, and I'll get 4/3 negative. So that's the slope of the tangent to that curve at that point. But the other way to do it, I could have gone and just plugged right in now that I've taken the derivative. I don't want to plug in here because all I'm going to do is prove that this is true. This point makes that equation true. But once I've taken the derivative, I could plug in and say 1/2 9 to the negative 1/2 plus 1/2 16 to the negative 1/2 dy dx equals 0. And this will be the number 1/6 if you put it in your calculator. And this will be 1/8. And then you can move the 1/6 to the other side where it's negative and divide by 1/8. And if you put that in your calculator, you'll get the same answer, negative 4/3. So you can do it all in general and then plug in, or you can plug in after you've differentiated implicitly and then solve for dy dx. And that is the end of the first day. So again, you may need to watch that a couple times or look back on it when you're trying your homework. But I want you to get through that homework this weekend so that when we start on Monday, we can look at some more difficult problems. So bring your questions Monday.